Physicists generally agree that the universe originated from a colossal event known as the Big Bang, which occurred around 13.7 billion years ago. Still, an enduring mystery remains. What triggered this immense explosion, and why did it happen? Over the years, scientists have deeply examined the history and structure of the universe, and the Big Bang has long stood as the most widely accepted explanation for the origin of everything we observe today. Numerous studies and the work of thousands of researchers have consistently reinforced this theory. The accumulated data repeatedly supports the idea that the Big Bang is the foundational event that led to the formation of the universe. According to the Big Bang model, dark energy, a mysterious force even more pervasive than galactic energy, is responsible for the continuous expansion of the universe. This energy works against gravity, causing galaxies to drift apart at accelerating speeds. The nature of science has changed significantly over time, especially with advancements in technology. New discoveries regularly challenge long-held beliefs, showing us that what once seemed absolutely certain may be incomplete or even incorrect. Recently, Japanese scientist Masanori Ie, also known as Mishoku, has brought attention to a potential refutation of the Big Bang model. This new skepticism is largely due to observations made by the James Webb Space Telescope, JWST, which recently detected 750 new galaxies that don't align with what was previously anticipated. These new findings have opened the door to fresh perspectives and deeper investigation. The JWST is reshaping our understanding of the cosmos by revealing galaxies unlike anything previously documented. You're invited to embark on this extraordinary journey beyond the limits of the observable universe to learn more about these astonishing new galactic formations. If you find these developments fascinating and want to stay informed about the latest cosmic discoveries, consider subscribing to the channel, giving the video a thumbs up, and sharing it to reach a broader audience. Also, turn on the notification bell to stay updated. The images captured by the JWST are breathtaking. Within a single frame, we can observe hundreds of galaxies grouped together, showcasing an awe-inspiring mix of beauty and cosmic power. While these images fascinate the public, they also raise serious concerns among scientists. The galaxies revealed by the telescope do not match theoretical expectations. In fact, the number of galaxies observed is far greater than anticipated, and their properties diverge significantly from predictions. These galaxies appear to be smaller, older, and more numerous than models based on the Big Bang would suggest. This unexpected data has stirred anxiety in the scientific community. One published paper even opens with the word panic in its title, highlighting the gravity of the issue. The galaxies do not resemble what existing models predicted. For decades, the Big Bang has served as the dominant framework for understanding the origin of the universe. The theory posits that roughly 13.7 billion years ago, the universe came into being through an enigmatic cosmic event. However, the new images from the JWST cast doubt on this well-established narrative. These extraordinary photographs challenge our fundamental assumptions. The galaxies seen through JWST appear too small, smooth, ancient, and plentiful when compared to what the Big Bang theory predicts. More troubling is the fact that these galaxies are 2 to 3 times smaller than those previously imaged by the Hubble Space Telescope, contradicting the expectation that objects should appear larger as distance, and thus time, extends backward. The smoothness of these galaxies is also confounding. According to the Big Bang framework, galaxies should exhibit structural irregularities due to turbulent formation and evolution. Yet many of the observed galaxies appear unexpectedly uniform and orderly. At the supposed origin of the universe, all matter and energy were compressed into a single, infinitesimal point, known as a singularity. At this stage, density and temperature reached extreme, unimaginable levels. The idea of a singularity is grounded in Einstein's general theory of relativity, which describes gravity as the warping of space-time by mass and energy. Within a singularity, gravitational forces become infinitely intense, and space-time bends beyond comprehension. It represents a condition where our current physical laws cease to function properly. In the context of the Big Bang, the singularity is thought to have existed before the universe began its expansion. This singular point, often referred to as the cosmic singularity, contained all the matter, energy, and basic components of the universe in a state of extreme compression. The entire cosmos was condensed into a space smaller than an atom, possibly even infinitely small. The density and pressure were so enormous that they defy our understanding of spatial dimensions. Imagine the whole universe squeezed into a spot too small to be seen. This is how profoundly compact the singularity was. In this scenario, gravity would have been so intense that no current laboratory could replicate the pressure conditions. Likewise, the temperature would have been so high that no ordinary form of matter could survive. Instead, matter would have existed in the form of raw energy and elementary particles like photons, quarks, and gluons, colliding with each other in high-energy interactions. At such extreme temperatures, the fundamental forces of nature, strong, nuclear, weak nuclear, electromagnetic, and gravitational, would have merged into a single unified force, a concept known in physics as the grand unified theory. This unified force would only exist under these extreme conditions. To understand this early stage of the universe, a theory that combines quantum mechanics with general relativity, often referred to as quantum gravity, is needed. But so far, no complete theory has been successful. The equations of general relativity, which work well on cosmic scales, fail under singularity conditions. Likewise, quantum mechanics, which governs subatomic particles, falls short in explaining strong gravitational forces. This highlights the need for a more comprehensive theory, one of the most elusive goals in theoretical physics. Another key aspect involves how these extreme conditions affect time and space. According to Einstein, space and time form a single continuum known as spacetime. Inside a singularity, this continuum becomes infinitely distorted. Concepts like past, present, and future may lose their traditional meaning. The extreme curvature near the singularity distorts time itself, making it difficult to understand or even define. This makes the singularity not only a boundary in space, but also in our comprehension. It challenges the very limits of scientific knowledge, pushing us into realms where even our best theories fail. When the universe began expanding from the singularity, it laid the groundwork for everything we now observe. Yet, the singularity remains a profound mystery, a point where the known laws of physics collapse and unknown principles take over. It's a reminder that, despite all our progress, some cosmic questions remain unanswered. The singularity was a hyper-dense, super-hot state where conventional physics does not apply, pushing scientists to create new models and frameworks that can describe such conditions. Until quantum mechanics and general relativity can be reconciled, the singularity, and what occurred at the very dawn of the universe, remains one of the greatest unresolved puzzles in modern science. This extreme environment featured temperatures so high they can't be replicated or measured with today's technology. The vast energy confined in that point became the seed for everything we now know. As this singularity exploded, the universe began expanding and evolving, giving rise to galaxies, stars, and planets. This expansion included a rapid initial phase, known as cosmic inflation, where the universe grew exponentially faster than the speed of light. During this short burst, the fabric of space itself stretched, creating the foundation for the structure of the universe we see today. Cosmic inflation played a vital role in shaping the large-scale structure of the cosmos. It smoothed out early, irregularities and distributed matter and energy evenly, making it possible for stars, galaxies, and planets to eventually form. Although the pace of expansion slowed after inflation, the universe has continued to expand. This gradual stretching of space, known as cosmic expansion, has been confirmed through observations like the redshift of light from distant galaxies, indicating that as space stretches, light waves lengthen and shift toward the red end of the spectrum. At the earliest moments, all matter was packed into a space so compressed that it couldn't exist in its normal form. As the universe expanded and cooled, subatomic particles such as protons, neutrons, and electrons began to form and interact with the surrounding energy. This phase, known as nucleosynthesis, was crucial in the creation of atomic nuclei in the first minutes after the Big Bang. Despite expectations of chaotic and deformed galaxies formed by frequent collisions, the images from JWST show organized, spiral structures and well-defined disks, galaxies that closely resemble those found in the modern universe. This contradicts the long-held belief that galactic mergers were common and necessary for galaxy growth. If these newly discovered galaxies have not undergone many mergers, it suggests they may have always existed in their current form, rather than growing larger over time. Furthermore, the predicted optical illusion of galaxies appearing smaller, as a result of universal expansion, does not align with what has been observed.